get started. Okay.
It doesn't.
All right, everybody, welcome to today's quick seminar. Today we're having the great pleasure of welcoming Professor Wes Campbell from UCLA Physics Department. Wes got his PhD at Harvard University, remember that place, with John Doyle working on trapping molecules. So it was his first foray into many of the A, M's, and O's that he works on. I met Wes when he was a postdoc working with Chris Monroe, where he transitioned into thinking about quantum computation, quantum simulation with trapped ions, and some of the pioneering work on that. That's really still used today. It's an important tool of using block lasers as a way of doing really high fidelity quantum logic gates. And Wes joined the faculty at UCLA, where he is now an associate professor. Wes is one of the most creative experimental physicists, has pushed the boundaries in all kinds of areas, from quantum computing to quantum simulation to precision measurements, measuring of the permanent electric dipole moment, and tests of beyond the standard model physics. And he's really, I've seen his letters of recommendation are amazing. What kind of physics he's done over the years, and he's a good friend as well. So welcome, Wes, your seminar.
Thank you. Very kind introduction.
Oh, by the way, I think you're now a fellow of the Mathematics.
Is that out?
Yeah,
Oh,
all
is
right.
it-
Yeah. It is now.
So let's go down.
Yeah, well, I just.
So I'm going to talk about experimental physics here mostly. So the first half of this talk is going to be heavily experimental. Apologies to the theorists for that. The second half is going to be a little bit more human theory and experiment. But it's important to understand the technical stuff. It's important to understand what's going on in the lab in order to provide context for why the second half of the talk is thinking about things that we're thinking about there. So I'm going to start off here with something that's well known to everyone in this room, which is the criteria that we look for in a programmable quantum processor, these qubit-Vincenzo criteria. And we typically start out with this first one where we need some qubits. And most of what I'm going to talk about today has to do with trapped atomic ions. That's one of the systems that I like to work with. They're actually very good qubits. You can argue with whether they are truly scalable or not. We have our own challenges associated with those things, but they, to some degree, certainly fit this bill. And that one is sort of, our first ingredient, right? Then we move on with this. We have to be able to initialize them, which you can think of as being kind of a measurement followed by a rotation. If you want to do a rotation there. Good coherence is sort of the time axis here. We want to know that we have good phase relationships. We need a universal gate set, which we can put on here. And I've talked to lots of people about that today here at Secret. And then we need our readout, which is sort of a little bit like that initialization step at the beginning, right? And when we do this with trapped ions, we typically do it in a way where if we project onto the zero state, for instance, the ion will not fluoresce when we shine a laser on it. If it's in the one state, it will fluoresce. So this usually shows up as kind of bright dots and dark spaces there. So that's kind of a real image of what that detection process is. Now the criteria 1, 3, and 4, or at least 3 and 4, I'm kind of throwing one in here, are things that I like to think of as being kind of the part that doesn't involve entropy of change in the experiment. All right, certainly 3 and 4, I think, fall in this category. So we've got a bunch of unitary stuff that happens in the middle of our algorithm. I'm not considering any mid-circuit measurements of this particular thing right here. And then the other two are the two that I'll call entropic operations. These are things where we have to somehow exchange information between our atoms and the environment. And those two are where I kind of spend a lot of my time thinking about, because to some degree that is, I think, one of the trickiest aspects of this business. It's a part of quantum computing where the fidelities are not good right now, and they probably need to be better. And so that's kind of where the atomic physics comes in. That's what I spent my time. Now for state preparation and measurement, this goes by an acronym, we call it SPAM. I'm not in charge of that. That was chosen before I came along, but I do like it. And for state preparation and measurement of these things, we have a few conditions that we need, but for our state preparation, we tend to use something called optical pumping. This is a bad nomenclature, okay? Optical pumping has nothing to do with a pump. There's no vacuum, involved in it. Really all we're doing is shining laser light onto our system, and we are doing it in such a way that it will gather population in a known place. And that's what we mean by optical pumping. And if we started off in some big mixed state here, the entropy went out with those spontaneously emitted photons. So that's kind of recoupling to the environment in that sense. That environment presumably doesn't have any tons of energy. So the system that we optically pump that we like to use for these, we want it to be a good qubit. And one of the first things that we look for in a good qubit is that we don't want it to be magnetically sensitive. Reason for that is there are currents flowing through all the walls everywhere, okay? And they're oscillating, which is even worse, okay? And you also have, quasi-static sources of changing magnetic fields in the lab. I know that some people have been able to correlate their qubit, the splitting in their qubit to the sun activity, like sunspots and stuff. I mean, it's really quite a
ionosphere.
Yeah. So you don't want to be magnetically sensitive. And so what we do is we choose two states whose quantum projection number is 0 on the lab axis, M sub 0 states. And so to first order, if you apply a magnetic field to those states, it's kind of, you can think of it as sort of perpendicular to them in some kind of generalized sense. They don't shift. It kind of has to go in quadrature. If you apply a large enough magnetic field, they will begin, the splitting will begin to either, become larger or smaller, depending on the system. But that's usually, requires a field that's larger than just sort of the ambient field. So we like to use those M sub 0 states. And if you're using an ion that is in the second column of the periodic table, missing one electron, and you want M sub 0 states, that means you need to have a non-zero half integer nuclear spin. Okay, because the J for the atom is a half integer. I need a half integer nuclear spin so that the total angular momentum of the atom is an integer. So I want them equal 0 states. And the smallest, kind of most minimal version of that you can get is a spin 1/2 nucleus. And these are very handy because it gives you just enough hyperfine splitting here so that I can define my qubit on 2 M equals 0 states. The splittings there tend to be pretty convenient from the technological perspective. They're not sensitive to these things. It's kind of just right for a minimal qubit. Okay. Now, to do the optical pumping, we typically drive a transition that goes from this F equals 1 state, ground electronic state, up to the F equals 1 state in excited state. And all of the decays I've shown here with wavy arrows are allowed, but the 3 that I've shown in blue go to the F equals 0 ground state. And that state is not coupled to the excited state legislature, at least not resonant. And so our population gathers in that F equals 0 state. And if you compare this to other methods for doing state preparation that people use in atoms, like one of them might be, well, I can gather everything way out in a stretch level where M sub F is equal to F by putting light that's polarized in that direction. That's one way to do state prep, but it's really tough to get a really pure polarization in the lab. You can get a fairly pure polarization out on your optical table, kind of part 10 to the 4, maybe at least over a short time scale. But once it goes through a window in your vacuum chamber, game's up, right? You get a big mess, right? Whereas all this requires is a wave meter. We just need to know the color of that laser. And if we set it to about, within about a megahertz of where it needs to be, we can do this with an error of kind of minus 50 dB. It's like 5/9 of fidelity. It's easy, it's fast, it's high fidelity. So which of these ions actually have this spin 1/2 structure? Again, we're talking about kind of the second column of the periodic table, the alpha and earth atoms, as well as the kind of honorary alpha and earth atoms, which is like the zinc family and deuterium. Well, the first one that you might come up with is cadmium. Unfortunately, cadmium ions, the transition there is quite far in the UV. Even worse is mercury. which is even further in the ultraviolet. Remember, the visible part of the spectrum starts about 400 nanometers. Okay? So the mercury and cadmium light is so blue that it's difficult to produce. You can't get a laser that will produce that directly. The only way to make that light is to start with lasers that are kind of in the visible and the red, frequency double, frequency quadruple, things like that. The best one there is terbium. And the terbium has an isotope, the 171 isotope, is a spin 1/2 nucleus, just like we wanted for this easy state ground. And the light is still in the ultraviolet, but it's not too bad. You can just barely get a laser, laser diode that works right at 370. That's kind of the limit. You can't really get one at 368. Okay, this is basically the bluest thing that they make. Okay, but you can just barely get there. It's sort of okay. It's the best of this, group of three things that are all bad.
So the fears, we don't think about this stuff. Why is it hard to make a laser at in the UV?
I think that there are probably materials things that come in to answer that question that I don't really know. I think there are also basic physics reasons why you can't make an X-ray laser, to do with pumping rates and things like that. But for this, it's strictly a technical thing. Like, why can't I do 368? I can't do 370. It has to do with whether you can make something that has that band gap that is lossless, or the loss is low enough that you can actually make a laser out of it. These things tend to also damage all of the optical materials they go through. So, particularly if you have high intensity, it will, call it solarizing. It will do things to your optics that will, create color centers and things in there, kind of turn them brown, basically over time. So it's a headache. So in dealing with this, and full disclosure, I use terbium in my lab. I like it. It's okay. I wish it worked in the UV, but I like it. We had a postdoc. So Eric Hudson is my partner in crime on this project here, and we had a potential postdoc, Dave Puckle. I knew him from Chris Monroe's group when he was a grad student, and he came to us and he said, "You know what? We need to stop thinking about things that are, limiting ourselves to what Mother Nature gives us." Okay, there are spin 1/2 isotopes of other ions, other than the ones I just listed. It's just that they're radioactive. Right? They're synthetic. Okay. And some of these are extremely radioactive, and you would probably have a hard time doing much with beryllium-11 for your quantum computer, right? But barium-133 is not too bad. That thing lasts for 11 years. And the operating wavelength of this is well into the, this is basically teal. Okay, that's the color of that laser light. And we can use all sorts of wonderful tools, like what Elohim has done in his lab, where they use fiber phase modulators and things like that. We can use telecom style photonics doodads with that light, which is not really possible for the ultraviolet. It's really nice. So, well, are we making something that's going to, cause a bunch of radioactive, fallout or something in the lab? The idea here was, let's find out. And it's easy for you to know how much of this material you have in your vacuum chamber, because you can take a Geiger counter up, right? You know whether you spilled it, because again, you can take a Geiger counter. You can find it. So how many atoms do you need? Let's say you're going to build the world's largest trapped ion quantum computer. And it's only going to use like 100. Okay? That is not very many atoms. Okay. We ultimately don't need Avogadro's number of these things that are vacuum chambers. This is the point. So you can go through the numbers on this, it's not too bad. So this is what the transitions in this atom look like. I'm going to show a few diagrams like this.
Wait, what's the lifetime of a graduate student in this experiment?
Yeah, it's about the same.
Okay.
So the transitions in this atom, other than this pink one here, are basically the color that I'm showing here. Okay, so it's like a rainbow, and all of that means that the technology is fairly easy for creating this light. If you are an expert in this, you might note that 614 and 585 are a little bit tricky, but I'm going to say that those can be low power, and so frequency doubling infrared light to create those wavelengths is really easy. It just works. Okay. So this is the structure that we're going to be dealing with. We're going to define our qubit down here on the n = 0 F equals 1 state and M equals 0 state, just like I said before. And then we have access to all of these transitions with fairly friendly and easy. So we like that these operating wavelengths are friendly. We like that the D states are long-lived. So this double D5 half state, the transition I've shown here, 1762 down to here, that is an electric quadrupole decay. And these splittings are not to scale. This thing is actually down really close to. And so that decay rate is pretty slow. It's about a minute for those D states to spontaneously emit and decay down to the S state, which is great because that's strong enough that you can still drive it with a reasonable laser, but it's weak enough that you don't really have to worry that much about spontaneous decay during your algorithm, right? And I'm going to keep coming back to this. Metastable states are used. We get our fast reliable state preparation from that qubit down there, which is a black state qubit. The problem is there isn't any. All right. We would love to use barium 133, but it doesn't exist. All right. And if it did, it would be radioactive. Now, that is obviously a solvable problem. You can create this synthetically. So what we can do is just buy something that has been neutron irradiated barium 132. Some of those barium 132 nuclei will absorb a neutron, and then they become barium 133. That's how they make that stuff, and you can just buy it. And in fact, they can send it in the mail. It's a small enough quantity, which I think is astonishing. So the way that this thing decays, just to kind of like, for anyone who might be curious, what happens in this 10-year half-life? Well, it basically swallows up an electron. The nucleus will pull an electron in, and a proton will become a neutron. It'll shoot an electron neutrino out of there, and it becomes cesium-133, which is the usual kind of stable isotope of cesium. The gamma rays and X-rays that are emitted when this occurs are not too nasty, actually. So the reason that we can buy barium-133 as easily as we can is actually that it's a standard calibration source for the device that made this plot for gamma ray spectrometers. People just use this thing for doing that, and so that makes it even more plentiful than if we had to, really get custom made, which would not be out of the question. But it makes it even easier, and it's not that bad for you. So what we do to handle the radioactivity is we keep the amounts low. We actually have lead bricks on our optical table as almost for show, for precaution there. We think that we actually just commissioned a new ion trap with a new chamber, and we're approaching the level where the total amount of barium-133 in there is like almost edible. Okay, really is not very much radioactivity. Probably the chemical problems with eating barium would cause you a bigger problem than the radioactivity. Okay. So we can do our state preparation of the F equals 0 state using that optical pumping that I showed you before. To make this spin down state, this F equals 1, M equals 0 state, we apply microwaves, and we use a composite pulse sequence to do this. And so this is some kind of a scan showing you, we want to operate at the top of that curve, and the point is that it's really flat.
What do you do right there? You get the sample in the mail,
Yeah, it's a good question. So we, in our chamber we've been using for years now, we put it onto a ribbon of platinum metal because we were going to do thermionic loading of the trap. If you desorb a barium atom off of a metallic platinum surface, it comes off as an ion. So the work function of platinum is higher than the ionization potential of neutral barium. So it's like thermionic emission, except it's thermionic emission of atoms, of atomic ions instead of electrons. We laser blade that now instead of heating it because the filament broke and it's not a complete circuit anymore. And it works pretty well. So basically, we blast it with a laser. It's a short answer for that. And then when you get in the mail, it comes as barium chloride dissolved in like an acid solution. So we kind of pipette it onto the file. Other questions? I'm glad people are speaking up, asking questions. Kind of, I don't want you sitting there. Let's address it. Okay. So our error to getting this composite pulse sequence to do the population transfer was about -43 dB. And the last step that we need to do to complete our state preparation and measurement, we've got this, we need the amp here, okay, is what we call electron shelving. So this is a technique that was, I think, pioneered by Hans Degel. The idea here is that at the end of our whatever we've done, and we want to read out our ion, we outcouple the population in this f equals 0, f equals 1, f equals 0 state, and we put it into the D5 house state. If you think about all the different arrows I've shown there and all the different weekly arrows and selection rules, you'll come to the conclusion that the population has to gather at D5 house. And that thing, remember, lives for about a minute. So we'll have plenty of time to subsequently look for fluorescence from the component state. And so this is a state detection histogram. I'll show, I think, a couple of these. But to help you understand what's being shown here, this is kind of the number of clicks we get on our photon counter when we're shining the light on the ion looking for fluorescence. And I made a histogram of that because we're repeating it many times. The blue histogram is for a case where we try to prepare one of the quantum states and detect it. The yellow histogram is for the case where we try to prepare the other one and detect it. And by setting a discriminator at that dotted line there, we can tell the difference between the two, including the preparation here, with an error of about -35. So we're not even really at 4 nines of fidelity. And single quantum gates are at like 6 9. So this initialization, DiVincenzo criterion number 2, and the readout, which is like the last one, these are actually places where we need to.
What's the answer?
That is a linear y-axis, same data.
Oh, I see.
Okay. Now, in real devices like commercial devices, such as this is one from, I think, IonQ, which is released by computing companies, they don't use barium-133. Although they are saying they're using barium now with yet undisclosed number of neutrons, but not when this picture came out. When this picture came out, we had not yet really done all this stuff, and they're using a terbium-175. So this is the isotope of a terbium that has a spin 1/2 nucleus. Again, kind of the minimal amount that you need in order to be able to define some of these things and make stuff really easy for you. So after doing this work with barium-133, one of my grad students, Tony Ransford, said, I think I want to come up with a scheme for doing this in terbium. And the terbium is more complicated. So let's give you a little tour here. I'm not going to ask you to go through all this stuff. Part of the point of this plot is it's got a lump. That's part of the point. There's not going to be a quiz. I'm not going to ask you what these things are. I don't want you to pay attention. Okay. Part of this is it's a big plate of spaghetti. Okay. But we get our, things that we get for a spin 1/2 nucleus. Challenges are, well, this light is 370, which is the main one we care about. Is in the UV. The D5 half state actually decays quicker compared to barium. In barium, it lasted about a minute. In a terbium, it decays in about 7 milliseconds. And it can go 2 places. It can go down to the F7 half state and down to the S state. And then it's a bit heady, which makes it, that's kind of a deep technical detail associated with trend. So Tony's idea was, instead of doing the electron shelving the way we did in barium, where we were driving to a P3 half state, we can do even better here in principle by using a narrow band transition. So this idea was we're going to drive this electric quadrupole transition at 411 nanometers. This is, again, a narrow transition that state lives for 7 milliseconds. And if we do that and we keep that light turned on, then eventually everything should fall into this low-lying doublet F7 half state. That's a unique feature of terbium ions. None of those other ions in the alkaline earth kind of family have this extra low-lying state. And then that state lives for a really long time. In the 171 isotope, it lives for about 2 years. Believe it or not, people have been able to drive that transition with a laser, which is pretty remarkable when you think about what the natural alignment of that transition is. It is an electric octopole transition, which is fun. So we demonstrated this kind of when we were doing a little bit of a different project using some mode lock lasers back in 2000. There was a group from Australia that picked it up and improved it a bit, and we decided to really investigate whether we can get kind of state-of-the-art fidelity with this. And one of our first expectations was, this is going to be great. We're just gonna leave the 411 nanometer laser on, and it's just gonna continue to clean this thing out. There's nowhere else it can go. The only place this population can go is either back down to these states, which we're pumping out, or down to here, using these selections, right? There was nothing else. So we did this and we started plotting this as a function of the illumination time. And what we found was that that data plateaued at some point, or hit a floor, however you talk about it, right? And the reason for this was that there was a decay mode that we had forgotten about. In fact, everyone had forgotten. No one had actually, noticed this or predicted it or mentioned that this was going to happen. It took us a while to figure it out. And the thing that happened is there is another decay. It's just that you never think about it because it almost never happens. Okay, it is possible for a magnetic dipole transition within the fine structure here to happen, despite the fact that they're actually quite close to each other. So it's a really long wavelength photon, and it's a magnetic dipole transition. So it's down by like alpha squared compared to the electric dipole transitions here. But when you go through the numbers, you find that once you start looking at the 4th decimal place of anything, you find stuff. Okay, so don't believe anybody who says, "Oh yeah, the fidelity." We're sure our fidelity. We haven't measured it, but we're sure it's 5 nines. Every time you look, I mean, basically the 3rd decimal place is where stuff starts showing up. Things that you should have anticipated, but you didn't, right? So it's always really impressive when people show something that actually has like 6 lines. They had to solve a bunch of problems on their way there. They're never going to talk about them because that's boring. We don't talk about that in the literature, but it's always really okay. So going through the numbers on this, it looks like that was indeed the case. We can calculate what that transition moment, it's going to mean in terms of that branching ratio, and the data was pretty much dead on there. And by repumping it, by adding one more color of laser, we can actually keep that from messing up our fidelity here. We actually make sure that that population is kind of reintroduced the proper way here. And what we find is that we can get that blue data point down there at the bottom. So we identified this channel, we were able to do something about it. And putting all these together, we get this as our photon cavity histogram for the terbium. And if you remember what the barium one was like, the barium one had these things overlapping. In the terbium, we could like drive a truck through here. And the reason is that the F state lives basically forever, 2 years. And the D state only lived for a minute. So you have a limited amount of time that you can actually look for fluorescence before you start to worry that 1 part in 10 to the 4 or something, the thing will decay. Doing this, we have the ability to discriminate the 2 histograms almost with arbitrary precision here. But our state preparation and so forth, those are really the limiting things. You'll notice these yellow ones, right? These are obviously pulled from the same parent distribution as the blue ones. So that's a state prep error. Yes.
So how long was the readout?
The readout itself, I think, was maybe 50 milliseconds. So putting all this together with our error budget, we think we kind of understand what the limits are there. This is a very slow technique, though. So this might be appropriate at the very end of a quantum algorithm when you want to read out a whole register. Okay. Someplace when you have time, you just spent a lot of time and a lot of effort doing a really difficult algorithm in your machine. You don't want to have to throw away your result because of finite measurement fidelity. If you have it registered n qubits and your measurement fidelity is f, then the probability of measuring it correctly is f to the n, right? It's exponential. You want to make sure that you get the right answer. That's a case where you would not mind doing this, right? If you're doing mid-circuit measurement, this is probably not your jam. You probably also don't need super high fidelity for this for mid-circuit. Okay. So the metastable states here, these were things that, to provide a little bit of historical context, when people started working with trapped ions and they were doing laser cooling in the early days and so forth, they were specifically drawn to species that don't have any metastable states. Because if you have metastable states that the atom can end up in, you have to do what we call repumping. And we're using this word pumping, optical pumping, right? You have to actually reintroduce it back into the optical cycling transition. And that means another laser, okay? However, these are, I am learning, it seems every year I learn this lesson, it's reinforced in a stronger way, that the metastable states are just plain useful. Even if you don't know what you're going to use them for yet, they end up being useful. If you get people working with these things and they're creative people and they're thinking about how they can use them, they're going to find uses for them. And that's exactly what, for instance, my student Tony did, right? You can do stuff with these. So thinking about these, with some of our collaborators, so this is, I'm talking about a collaboration with Lincoln Labs and MIT and University of Oregon, all the ion trap folks at those three places. We were thinking about this and we came up with the idea that using the metastable state as a place to house the qubit seems like just as reasonable a thing as using the ground state or as using an optical frequency transition. And you have effectively different species. If you think about this F state, if I were a particle physicist, I would call that some other particle, right? It's some excited state of my particle, and it lives longer than anything I care about, right? I would call it something else. It actually has a slightly different mass, even, right? We're not particle physicists, we still call it a terbium, but it is chemically, it's a different species, right? I mean, it is basically a different atom for all of our purposes here. And we can get rid of some of the dual species stuff that's been going on in ion trapping, where people actually have to build a whole ion trap system with all the lasers in such a way that they can use both calcium and strontium, or something like that, so that they can do things like sympathetically cool their data qubits with these other ones, so that they can do readout and stuff like that. So all of these tasks for which the dual species platform has become so popular can basically be mitigated to some degree by using these metastable states. And you get rid of some problems. One of them is some of your laser complexity might go away. Shuttling of dual species ions is annoying and difficult for technical reasons, but they are nonetheless limiting and important. Interspecies gates between the two different species can also have difficulty, particularly with the mass mismatch between them. And then you have to worry about which order they're in and so on. So we decided to supplant this and say, well, let's just use one species, and we can essentially define on the fly what the role of each ion in our trap is going to be. So we can load all the ions into the trap, say you're going to be metastable, you're going to be ground state, you're going to be an optical qubit, whatever it is, and we can change those definitions as we want without having to physically rearrange the ions. Right? You can basically match form to function here. So if there's a state that's good for storage, we turn them all into that state when we're storing them. If there's a state that's good for gates, we turn them all into that state for doing our gates. That's the idea here. And so we have the optical frequency O, the metastable M, and the ground state G qubit, which we call the OMG blueprint. This is one of these things that start off as a joke. And then we were like ready to submit the paper and no one had changed the title. So I was like, all right, let's do this, guy. I don't think Dave Wyland is all that stuff. So we can basically use these things and take advantage of it. It allows us to do this modularity. We can decouple them. So for instance, the ground state, the light that I'm going to use to drive my gates for the ground state qubits might be essentially invisible to the metastable state and vice versa, right? And then instead of physically moving things around in space, hopefully we can get rid of some of that by just moving around on the internal states, right? You can call it Hilbert space shuttling. That's also kind of a little bit of a joke, but the basic idea it's okay. So the metastable qubits, though, were not something that was well developed, and certainly not in terbium. So this was in my group. We had been playing with this F state for a while, and we decided to go ahead and try to, let's make some state preparation and measurement. Let's see how well this thing works. So the way that we can do our measurement, for instance, we can clean out one of these states using a laser, and then we check for fluorescence in the ground state. And the splitting up there is a pretty convenient place technologically, and using this to herald the state preparation. So we can do this if the ion is bright after doing it, and we didn't make the metastable state, we can try again, right? Once the ion is dark, we know where it is, right? We can herald that state preparation. And so doing this, we get pretty good fidelity for our state preparation up there. The actual operations on the qubit, I'm showing you some kind of, we apply resonant microwaves, Rabi flops back and forth with really high contrast, so that thing works pretty well. These are m=0 states, they're non-magnetic. So kind of essentially right out of the box. The thing. Another capability that we have here has to do with the measurement. So one of the things that we can do here is a projective null measurement. The idea of a projective null measurement is I can clean out one of those 2 qubit states with my laser and then check to see if there's any population down there. And if there's no population down there, I know that the ion is in the other state, right? So you can think of that as like probabilistic quantum non-demolition, if you like that sort of terminology. Doesn't really matter what you call it, the idea is fairly simple. So if we do that, if we start Rabi-flogging, we prepare a state up there, we start Rabi-flogging, and then halfway through, when we're kind of in an X eigenstate, we then perform one of these projective quantum measurements on a random choice between the 2 qubit eigenstates. And then we keep going with the experiment conditioned on having a dark ion. What you're going to see is that we don't get any contrast from that point. Hopefully that's appearing yet. There we go. Okay, so that's these tail circles here, right? However, if we then go through our data and we say, okay, for run number 14, the state we cleaned out was the upper state. And we bin all those into one data set and we take the ones for the lower data in the other data set. You can see what happens here. We actually take a spin, we orient it along the x-axis, we measure it in the z basis, we then keep going with this, right? You can do the opposite thing. You can start it in the x basis or the z basis, measure in x, it all works. So it's kind of like as a little toy for thinking about measurement schemes and things like that. It's a nice kind of didactic, I think, example of how these projective measurements. Now, this is actually, not just for fun. Actually, we have some aims here associated with quantum computation. So to get into this, we can think about the computational Hilbert space of some device made up of qubits. And we usually think of it as having this tensor product structure of qubit subspaces. And that's, I'm not going to claim that's the magic sauce of quantum computing. So I'm not going to claim I understand what the magic sauce is, but it's really good. Okay, it's really powerful, it's really helpful. It's huge, right? And we have kind of, knobs to make changes to the Hilbert space that are manageable. But really what we have in our system is not just a tensor product of qubits. We have tensor product of atoms. Each atom, they're all identical. Each one has a whole bunch of states. In principle, you can have access to those states. And so, one of the ways to think about how to characterize the kind of error correction scheme is to imagine that your total Hilbert space has some subspace where you have your code words, right? You have some computational subspace. And then you have a direct product with some orthogonal subspace where the error products are going to live, right? Where when you have some kind of an error, it's going to cause a transition into this orthogonal subspace. You can then check the orthogonal subspace and look for errors, right? And so using, since we don't just have a bunch of qubits, we have a bunch of atoms, they have a bunch of states, we can do things like this. So one of the ideas for that is something called certified quantum gates, but here you can come up with a scheme for doing single and 2 qubit gates with trapped ions, where you are checking using this kind of projective quantum measurement thing for the errors. Okay, you turn an error of a known kind of characteristic into a transition into an orthogonal subspace. That's the trick. Once you've done that, the rest you can do. Read it out. Look for population there, right? And then read that thing out. This is another thing that we can do is turn kind of mundane, hard to deal with errors into what are called erasures. Okay, this was not terminology that I knew. When I wrote this paper over here, I didn't know what I was doing was called erasure conversion. I just didn't know that in the literature, but that was pointed out to me later. That's what that is. Okay.
That was during the golden age. We decided that anything that happened there is the golden age.
Okay, nice. Nice, 1997.
Yeah.
Okay, cool. And then, since that time, this idea of doing erasure conversion using metastable states has also kind of taken hold in the community of people doing stuff with neutral atoms as well. So how does the erasure conversion work? Well, here, if we have an atom, whether it's neutral or an ion, or I find a qubit in the ground state, I need some laser to do something. whatever it is. Maybe it's the trap laser, maybe it's a gate, okay? I'm somehow leveraging a dipole moment between G and that excited state. And if there's spontaneous emission here, and spontaneous emission goes back to my qubit subspace, that can be like a Pauli error, right? That can flip my qubit. Okay. Or if it goes back to this G state in general, it's actually a little hard to tell the difference between the qubit states and the other states in the G manifold. Okay. It's not impossible, but it takes some work. Well, what if we do everything in the metastates? That's the idea. Here, if we have a spontaneous scattering event, and it is likely to go down to the G state, that's identifiable. That's an erasure, which means that we know where the error occurred. We know which qubit, which ion actually had the error happen. Okay. And if you go through how you deal with that, you could reintroduce it as a mixed state back into the qubit subspace. That's actually easier to recover from than a leakage error where you don't know where or a Pauli error where you don't know which ion had the Pauli. And so working with Ken Brown and his grad students, Ming Yu Kong, we've decided to look into this, try to figure out whether this really is an advantage. Now, the first case that we could consider in terms of our assumptions is, what if the total scattering error is the same in both cases? And that was what I think that neutral atom paper I showed on the previous slide basically was. They said, well, assume that the scattering error is the same in both cases, and then you win. You win using the OMG scheme in that case, because a lot of the large fraction of those is now an erasure, right? You can convert that, right? And then reintroduce that thing. However, the dipole moment you're leveraging for this transition, which is the thing you're trying to do, is only a fraction of kind of the A coefficients associated with that excited state. So you paid a price for this. The price you paid is that this transition is weaker. So you need to either make the laser stronger or get close to resonance or both. And they, I think in that paper, they kind of just assumed the errors were the same. They said this is something, right? So we can try other assumptions here. And this is ongoing work. I'm not even going to show you the results, but one of them is that we make the Rabi frequencies the same, the gate times the same, I should say, and we make the laser intensities the same. The other possibility is that we make the gate times the same and we make the laser detunings be the same. And we allow the laser powers. And you could argue that one corresponds more or less to the scenario that you have in your own lab, whatever that is, and the results of whether the kind of metastable scheme actually is advantageous. So far, it looks like it depends upon, that's what we'll say, it depends upon which of those cases. So there can be cases where there are advantages. It's not quite as simple as saying, hey, the scattering is detected.
Let's just not, don't remember the details here. So at the end of the day, one can convert these erasures to a kind of arbitrary Pauli error. And I mean, you start here the rotated surface code. So which is typically we assume nothing is lost, so to speak. So
well, yeah, I mean I think the simulations that Ming Yu is doing are including leakages as well.
Okay, actually. So there's leakage, but somehow that's addressed here.
Well, if you have leakage, like in this scenario, if you have leakage, then it's just leakage, and that's pretty bad. Right. The hope here is that by actually reintroducing those qubits into a mixed state, it's no longer a leakage error, it's a different error.
That's right. Okay, that makes sense.
Okay. So waste management, let's talk about resources. The state space here is actually pretty big, right? We have many different levels. And of course, this is vanishing a small fraction of the actual levels in the atom, right? For the most part, what I'm going to be talking about in this part of the discussion is actually only the long-lived states. Those are the ones that tend to be most useful for actually storing and processing long information. Okay? The other ones are useful during that process, but we don't tend to move the information into those states, at least not for very long. Now, this metastable state has quite a few levels in it. This is I equals 1/2, right? The nuclear spins 1/2. We have J equals 7/2 level. But we found uses for some of those states already, and we decided to get greedy and say, We want more spins. We want even more states, especially if you can get more clock states. We only have 2 there. It's just a qubit if I really require m equals 0. In the terbium-173, however, there will be 6 hyperfine states. And as a matter of fact, these levels, nobody's ever measured. They don't even know what the order of the splitting is. There's some theory that's been done on it. It's not actually known. In fact, there's controversy in the literature about what the magnetic octopole moment of the actual terbium-173 nucleus is. And the disagreement in the literature is 4 orders of magnitude. Okay, so obviously somebody messed up there. So we set out to measure this. We're going to measure this. We're going to clear up this 4 order of magnitude disagreement in the literature, and we're going to get 6 clock states out there. That was our goal. But we don't know what any of these things are. So this is the state of affairs when we started working with this ion. This splitting was known, that splitting was known, but nothing else was known here. The rest of this kind of shown in brackets. Now, the problem with doing spectroscopy on single ions is that when the ion gets optically pumped into some dark state, you don't yet know how to repump it. It basically boils out of the trap. There's background heating of some sort, and you lose it. Okay, it goes out of the trap. So the students call this depthtroscopy. Right? And performing our depthtroscopy of a terbium-173, which is pretty, I like it. It's got kind of heavy metal around there. This is where we are right now. We've been able to figure out what the splittings are in all the states that are shown in red here. We've measured those. It's been a little bit painful because again, the ion dies, it goes away when we do this. And we even have one of the splittings in the F state. So we don't yet know the full structure there, but we're kind of still working on it. And you know, if you're willing to work with some of the Zeeman sublevels here, there's I don't know, there's like 49 states here, or like 50 states. And they all live longer than your computation. So it's effectively we have this multi-level system, but it's connected to the easy to use part here, where we can do fluorescence, laser cleaning, all the things we know how to do. We know how to connect those two. So this is kind of our paradigm. So thinking about use of these resources, these multi-level things are not just a qubit, right? This is, I think, preaching to the choir here at Secret, based on conversations that I've had. Lots of people here are, I think, saying the same thing, realizing the same thing. That we have lots of levels, we should use them. And if you think about how atomic processors work, whether it's a Rydberg tweezer system or trapped ions or optical lattices, they tend to actually be limited in the number of atoms that they can actually work with in a high fidelity computation. Right? The reason that we don't have thousands of qubits in these things is basically that they can't work with thousands of atoms and still keep things working well, right? It's not that you run out of atoms, you run out of technical stuff, right? Track zones that you can work with, whatever it is, right? There's a whole list of these things. We're atom limited. And in the case where we're atom limited, maybe it doesn't make a ton of sense to actually use just 2 states.
Okay, so Bazan, do you mean phonons here? Or what do you mean?
So for trapped ions, I mean phonons. But for something that's using like superconducting, whatever it is, it could be other stuff. But the thing that happens is you get crowding of those modes in frequency to get okay. So quantum computing, these things tend to use entanglement or so, a lot of people say. So we had our Nobel Prize recently, it was talking about entanglement, right? This was looking at non-locality. John Clauser did this measurement where they're showing that we can violate Bell's inequality. Alan Aspect did it in a way that was a little bit closer to kind of closing that locality loophole, right? Showing that you really do get non-local correlations here. Anton Zeilinger did, many things in this field. This is kind of depicting the one he did that was closest to these other 2 for artistic reasons. I think this is why they did that one. But this was last week. With this, we have these non-local correlations. But I want to point out this paper by Secret Superstars, Robin, Carl, and Ivan, that I read. Ivan pointed this out to me, and it really changed the way I think about how we're going to use our resources in our quantum computer. And what these 2 papers here are kind of pointing out, among other things, is that you don't need the non-locality in most quantum computations. There's no part of Shor's algorithm that asks you to do a loophole-free, space-like separated operation within your machine, which is good because your machine, these things are like microscopic distances apart, right? you'd never do it. It would be a mess, okay? So we don't have to put individual qubits into individual separate atoms. I don't need a separate atom for every qubit that I have. That's the point, okay? That I don't have to, since I don't have to do the Snell's inequality measurement in a loophole-free way, I'm free to actually use, multiple qubits per atom. So far, if we want this computational Hilbert space to look like a tensor product of our actual two-level systems, but what we have is the tensor product of identical atoms, we can work on how can we turn these identical atom Hilbert spaces into something that is going to allow us to have that tensor product structure. We want operational access to the atomic Hilbert space in a way that looks like a tensor product structure. Okay. And we, we're obviously going to have some other things too, right? We have something that's the size of a power of 2 here, so that we can factor it in some other final substance.
So why multiple qubits in an atom versus a qubit?
So this is a great question. Something we talked about a lot at lunch today. The reason I like multiple qubits per atom is because while I can't prove it, it seems like an efficient use of resources to me. But you can also, if you can do measurement and state preparation of one qubit within an atom without disturbing the other one, it's now just a drop-in multiplier for your number of qubits in your binary quantum processor. So you can do things like error correction, your qubit-based quantum error correction, your regular algorithms are still going to work. It's open for discussion. It's good. It's a good question. So
It goes well with green chili. So.
yeah. So if we have four levels of our atom, and I'm going to assume for this discussion, I'm going to label them through scores here. I'm going to assume that the splittings are all different. Okay, I'm not going to worry about degeneracies there. They're all well separated. The hierarchy of energies is not important here, right? We're just going to represent them using something. Okay. We can think about how this is going to work. Now, I can have operations that couple levels together in a pairwise fashion. And these are not really Pauli operators here because they kind of have zeros for all the other parts of this atom state space, but they're kind of like Paulis. Okay? And if I have a pair of them like that, I can think of that as a way to decompose the Hilbert space as a direct sum of two-level systems. Okay, but that's not unique. I could also have coupled them this way or across the diagonals. Those would be different direct sums. Okay, they would all kind of have the same dimension, etc. But you just be talking about how you slice that up and be slightly different. So that's not really 2 qubits. It's not multiple qubits. It's not p qubits, certainly. But it shows you something about the resources that you're going to be using here. They are going to be exponential in the number of qubits I want to encode per atom. Right? And that is not a good way to scale your quantum computer to match a problem size. You can't just do your quantum computation using a single atom with jillion states. Okay? That isn't going to grow with problem size the way that you want. This is the big point of the paper that Ivan and Carl wrote. Okay? So that's obviously a loser here. Maybe there's some in between, maybe 2 qubits per atom, maybe 3, maybe 4, something like that. But you do pay a resource cost. So the idea here is that we will scale our system to meet the problem size by adding more atoms, but we're going to increase the slope of that by making each atom hold more. So here's how the encoding works. You don't say that this is a qubit on the left and this is a qubit on the right. That doesn't work. That doesn't have that tensor product structure, right? Instead, we assign each of these states as a tensor product of 2 qubit eigenstates. And I have what I call like the horizontal and the vertical qubit here. Right? The horizontal qubit is kind of left versus right. Okay. If I ask a question, if I do a measurement, is it on the left half versus the right half? That's a projected measurement on the horizontal qubit. If I do that in a way that doesn't give me up-down information, it doesn't touch the vertical qubit, and vice versa. And so my Pauli operators for the actual, qubits, for my logical operators here, are just the sums of those kind of atomic.
All right, I have a very basic question. So usually when you have all those levels, like people just draw some lines, right? And it's not like a complete graph. But I guess in principle, you can always jump from one state to another state if you have the right frequency or.
You could,
So here, this is also supposed to be, like, actually supposed to be a complete graph where like 1 and 2 and 0 and 3 is also connected by some frequency, but you're just ignoring it, or?
we don't really need them, so I haven't put them
Okay,
on
okay,
there.
right, yeah, in this case, you don't need it.
This is one choice of a minimal set.
Right, got it.
So the kind of minimal structure that I need to make my way around this thing as if, kind of mimic a sort of tensor product of qubits is like a hypercube graph.
Right.
Adding other diagonals and stuff might also help you, but it's not.
So
And
like in
necessary.
this setup, I guess you would originally have like 6 bonds that you can think of in terms of constructing a square like this, but you just choose one that's somehow the most convenient. And
Right.
and then you end up in this kind of.
Right, exactly. As long as I've made, some slice of a hypercube, then I can get anywhere that I.
Right.
But you're absolutely right. You might be advantageous in some circumstances to be able to drive diagonals. Okay. So how are we going to do the state preparation and measurement? I told you that I, was interested in the idea of using qubit-based quantum error correction. So I want to be able to measure one of the qubits in an atom without actually disturbing the spectator qubit in the same atom. What we can do is use an ancilla ion as our actual. We're going to do laser-induced fluorescence on this at the end, right? This is where the entropy is going to come out, okay? But what we're going to do is add energy to the motional. These things are trapped ions. They're in a trap. I didn't really go with this. They're in a trap together. They repel one another, so they form into this Coulomb crystal as normal modes of motion, right? We can pull those down to the ground state, and they're harmonic oscillators. We call them phonons, right? We can put a laser on that couples the one state up resonantly to an excited state. The laser can have a beat node at a phonon frequency. If we do the same thing to the 3 state, same strength, same phase, it will also add energy to that phonon mode of motion in precisely the same way. And in that way, we can add energy to this thing only if the vertical qubit is in the other state. We do it without gaining any information about left-right, about the horizontal. We can do the same thing for the horizontal qubit, similar scheme, right? It generalizes pretty easily. We then subsequently ask this ancilla ion, was energy added to the motion? Which is something that we, okay. So that's going to give us our state preparation and measurement. For 2 qubit gates, there are 2 qubit gates that will exist just kind of within, in intra-atom 2 qubit gate. That's trivial, basically. It might be nice to have, but if I drive just one of these atomic values, for instance, I think that's usually a 2 qubit gate. It's pretty straightforward. But the harder thing is we want ion to ion 2 qubit gates. And I want to do it in a way that doesn't actually disturb the spectator qubits on those ions. And the way we do it is simply by using the exact same gate that we do with regular mono-encoded atoms, qubits in them, except we use these Pauli's instead of the kind of native interactions in the atom, right? We just use our actual. That plot is only for the experts who know what those plots are supposed to look like. That's a trapped ion. Then you stop in the middle and it makes a bell state. And this is another kind of gate. It's called a ZZ gate. Same idea. So they work just like they would, for mono-encoded atoms, at least at the level of, in silico. Okay. So we have all of our criteria that we needed here, and now we only need a few qubits to do it. And that might be nice, but I think really the more exciting thing is, well, we've got all those other qubits. We can now do a bigger algorithm. Pretend like this is a bigger algorithm, not 2 copies, just one. Okay. So what about 3? We do 3 qubits in an ion. Yeah, we can do that. It starts to get a little hairy though. And, each of these atomic Pauli's now requires each of these qubit Pauli operators is now 4 transitions, 4 atomic Pauli's. Okay? So you can start to see the resource cost here is starting to grow. But with these tools, we now, basically have this access, the operational access. We have paid a price though. The price we've paid is that we need, the number of kind of edges is on our hypercube base. We need that many actual atomic calories. Whether that is an expensive resource that makes this not worth it, or whether that is perfectly worth it, is a question I think for the experimentalists. It's kind of an open thing. This is basically your control parameter cost. Okay. So just getting back to this, by doing this, all of these bullet pointed items, basically we can now increase the number of qubits without actually affecting qubits. We've been able to increase the kind of computational power of an existing machine, because these are already in the machine. Okay, all these states are already in there, right? In most of these machines, they're just being ignored. So what we've done here, just to kind of review here, is we've taken something that had a qubit encoding. We've introduced this thing that I'm calling a polyqubit encoding, where the atomic subspaces go, have dimension of 2 to the p, but we pay this price and control cost to make it look like it basically behaves like a tensor product structure. This could be a good bargain in the near term. It's probably, it's not a way to scale really. All we're doing is changing the slope. Okay. But if you're atom limited in the near term, this is a way to actually get somewhere. So we can use our standard algorithms, including qubit-based quantum error correction. This gives us more qubits. The connectivity is also increased, as it turns out. So if you have something that, like for instance, you only had nearest neighbors, well, now you have like 3p minus 1 nearest neighbors, each of these things, because you've got qubits that live right on the thing. That reduces the need to actually shuttle the ions around and things like that. But this is kind of, I think, the best thing is that it's already there. People are just ignoring the states. I think folks should use it. So it's always a good idea when people on your team are getting license plates and tattoos. So these are I think mostly I will list of all the hardworking folks here who really did all the work here. Much of this was done, of course, with Eric Hudson, my frequent partner in crime, and that's it. So I'm happy to answer questions.
Any questions for Wes?
Yeah, I guess, how does, if how does this, multiple qubits per atom change the errors that you're experiencing?
I don't know. If you have an error that is, it's one of the things we usually assume in error correction, that is local in space, right?
Yeah.
Then it can affect, yeah, exactly. It can affect all of the states within a certain atom. And to some degree, those could be picked up by all of the qubits, depending upon the nature of that.
Right, you're not correlated errors.
Yeah. I think that's a great question, and how to deal with that is an interesting and open one, for sure. I don't know. Yeah.
Question. So is it with the usual, those Momo-Sorensen-like curves you were showing, clear how to do, if I want to do the particular entangling gate between any of these qubits within, so I can have entangling gates between the qubits within an atom, and then
Within a single atom?
yeah, and then also entangling gates between whatever I want to do the specific qubits that are between different atoms. Is that all straightforward to do in this case?
So the intra-atomic 2 qubit gates are just microwave transistors.
Right.
That's
They're
straightforward.
just
The interatomic ones work just the same way as the these Moller-Sorensen schemes or whatever. The only difference is you're applying multiple tones simultaneously, much like the state detection. So this plot shows you what happens when you do a Moller scheme using this operator instead of just one of those. What you're doing secretly is more like that. This is the ZZ gate version, but imagine that this Raman transition actually connects 0 to 2, that one connects 3 to 1. That would be a Moller gate on that horizontal qubit with potentially some other ion. So they seem to map onto each other. You have to match some things though. So we've looked at that. For instance, I need the phases and strengths of those derived one. For the XX gate, I don't need the strengths to be, I need the strengths to be equal and the phases the same. And so we've done some numerical studies. What happens if those are off by 1%? It's actually not bad.
Great. Any other questions? Yeah, Shiva.
So when you talked about this conversion to data, so what is the difference between the qubit encoding the ground versus the metastatic? How does the conversion to data?
In the ground state, it's hard to convert it into an erasure because many of the decays go back to the ground manifold. And almost none of them go to the long-lived metastable state. So if you want to convert into erasure errors in that scenario, you need to do your gate, move all the population from your qubit subspace into the metastable state. Move anything that was up there back down to ground state, then look for fluorescence, and then undo that. And we basically assumed that that was not going to happen.
So you just thought that in the qubit sample testing that can be done. Also in game.
Exactly. It's really easy to just shine a laser on and see if anything's in the ground state. That's like
But then what is the issue with doing that? Why the approach
the reason that it may not be a win is that you might have to apply stronger laser light or closer detuned laser light to run your gate. So you'll probably have a larger total spontaneous scattering rate if you're starting in the metastable state than you would in the ground state. However, it might still be a win if you can,
But still the errors are only variation. So still you can detect that. You can easily cut because that's like you also know the location of the errors. It's better be.
right, but there will also be decays necessarily that go back and it'll be Cowley errors, for instance. There will also be leakage errors. There will also be decays that go back to that D state. So let me go back to this picture and be quick about this. I think I did. So when you're in the metastable state and you're driving this gate, I showed it like the only decay that was possible was down here. But that's not true, because if that were true, then this transition wouldn't be possible in the first place. That thing I need to run my gate. So there is also a probability that it comes back to the metastable state, because there has to be a transition dipole moment there, or else my gate wouldn't work.
So there's also a lot of Pauli errors
So you can also have some Pauli errors here, right? Exactly.
on top of the erasures.
Exactly. So at first glance, you say, "Oh, this is going to be great. It's going to win." It depends. You gotta look into it.
Why is the minimum like set of operations to do like intra-atom gates represented by like the hypercube instead of being connected graph? Shouldn't you be able to do like a complete intra-atom gates as long as you can you have like a connected graph?
If you're willing to do fully connected, you can certainly do that as well. That's only kind of increasing your
Not fully connected, but any just connected graph where it's one connected component, like a line graph.
Oh, there, I think you're going to end up taking many, many steps to do the thing you want to do.
Yeah.
So whether you want to think of that as multiple transitions or not is maybe another case. But that's what I would say about that. I think in principle you can do it. But as long as I can somehow or another have this state, kind of talk to that state down there, and I can do that arbitrarily. You can do what you need to do. It's a question of how hard it is and how much you have to do to get there. The most kind of conceptually straightforward, I think, is to imagine the edges of a hypercube. In terms of atomic structure, that's also sort of like the easiest one for me to imagine in the structures that I'm thinking about. But I think you're right. As long as you get wherever you need to get, then you can make a complete gate set.
Yeah, hypercube isn't like strictly minimal. That's what I'm asking. Right. Okay.
Right.
Carl. So, it seems to me that you've got a fairly high dimensional open space on which you introduce a artificial tensor product structure. You are one. This is really important. But one, you are kind of restricting your thinking about what kind of gates will be the best ones for universality. But you be restricted to think about single system gates in your case, single qubit, two qubit gates. And those may not be at all the natural things that you do in that kind of system. And I think the flip side of that is you introduce an artificial tensor product structure, and all the error models for that are going to be nothing like what people usually assume for tensor product structures, that is single qubit errors and two qubit errors, because the errors don't know nothing about your artificial tensor product structure.
I think I agree with those. I mean, I might say even further that even for kind of qubits that are individually hosted on individual atoms and so forth, the error models are also not.
Yeah, but not in quite the same way, because to say that qubits hosted on this atom and a qubits hosted on this atom, say the errors are single qubit errors, is a heck of a lot more convincing than saying you've introduced into a four-dimensional subspace a tensor product structure. And that those errors are going to respect your tensor product structure.
It's possible. I mean, I think there are cases where you can imagine it actually would. So if I think about, for instance, errors in my control, right? Like the pulse area that I'm applying is not the right pulse area, something like that. Well, I'm driving through four of these transitions simultaneously, in this particular example. You expect that error probably is common mode all four of those times. That would be a single qubit type error. Okay. Now that's not the only type error that can occur, but that would really only manifest itself since the vertical qubit as an error.
So I guess what I'm saying is, whereas you have a real tensor product structure that is self-consistent, error models can be, you could analyze error models at different levels of complexity with some convincingness they apply to the system you're describing, whereas it seems to be the error models for your tensor product structures, they'll just be totally new things that will have to be analyzed in new ways to see what kind of error correcting codes are effective against. You won't be able to rely on what people are down. It'll just be different.
Yeah, I think I agree.
And maybe we should be doing that anyways.
Why?
And maybe we should be doing that
Maybe you
anyways.
should be doing that anyway.
Yeah.
Yeah, I mean, there's no reason, the reason to slice it up as qubits is basically to use it as a drop-in, multiplier for existing systems where people learn qubits. But I completely agree with you, and there's no reason you can't slice the thing lots of different ways. It could be, a prime, the size of the space could be prime, right? You do all kinds of things. I think if we think about how to do partial measurements on systems in this context, that might also be fruitful for error correction instead of having to collapse the entire atomic, state onto one of the eigenstates. That might be kind of an inexpensive operation, but I don't really know.
All right, well, I think we should thank Wes again.
Actually, Ivan, before you go, I have a silly question.
Yeah, okay.